Hi there, welcome to my Puredata tutorial. In this tutorial we're going to be making a program to carry out a function called Wave Field Synthesis. If you don't know what that is, basically it's a spatial audio technique where we use a large array of small speakers which are placed really closely together to synthesize a larger wavefront. The idea is that you can use this to create virtual spots around a room where sources appear to be coming from, as opposed to them coming from the speakers themselves. So there's a few things that we need to look at in this programming language. The first thing that we really need to be looking at is getting the wave field synthesis to work. So we can ignore point 1 on this list first of all, which is to load the files into the program. What we're going to look at first instead is these 2 points here, points 2 and 3, which basically explain how to achieve wave field synthesis. So what these mean is that t equals d divided by 340. So the 340 is the speed of sound. D stands for the distance between any source that you want to have in the room and the speakers, and t is equal to time. So we divide the distance by 340 to get a delay time, which will add to the signal coming out of the Puredata program. Point 3 is about amplitude decay, which is how much the volume level deteriorates over distance. And to calculate that, we do the frequency divided by the distance squared. So we take the distance of the source to the speaker, we square it, times it by itself, and we divide 1 by it to get the amplitude decay, and then we turn the volume up the appropriate amount to cancel this out. So to start with, we're going to have to look at a few basic Puredata functions. If you don't know what Puredata is and you've just stumbled across this, it's a programming language that uses objects and data flow between objects to carry out functions. We use it a lot in audio because it's quite good for passing audio around and working with audio. So the first thing that we're going to do is we're going to get some signal through the system. So ignoring that point 1, which is load files, we're going to use this object OSC followed by a tilde. OSC stands for oscillator, so we're creating an oscillation or a tone generator. The tilde is what we use whenever we're dealing with signal in Puredata. It basically tells the program to expect, or the box below it, the object or the message box below it, or the output, to expect some sort of signal flow. And then we're going to put in 440, and that stands for 440 Hertz, which means we've just made an oscillator which will oscillate at 440 Hertz, which is the frequency that it's going to oscillate at. So the next thing we're going to do is put in this object here, which is going to be a multiply object. So there's various mathematical functions in Puredata. This one here is going to multiply the signal tilde by a value 0.05 to get some volume out. So the way a computer works with volume is any value between 0 and 1 is equal to a volume, 0 being absolutely quiet and 1 being full whack, no more above 1. So we put in 0.05, relatively low on the scale. We don't want anything to output this like ridiculously loud. So what we're going to do is we're going to take the outlet from the oscillator object and we're going to feed it into the inlet of this multiply object. So what it's going to do is multiply this signal by 0.05 to raise the level a little bit. And then the last thing that we're going to do here is we're going to put in this. This is the DAC object, which stands for digital to analog conversion, and basically that is how we output sound. So if I click here, you can see there's two inlets here, one for left and one for right. All we're going to do is connect the output from the multiplication down to the input there. Right, the next thing we're going to do is turn on the DSP for pure data. This allows us to have audio coming in and coming out. It's the digital signal processing. So we put this on and there's the oscillator. You can hear it. It's right there. We'll switch it off because it's a bit annoying. But you can see we've got a signal out there. So what we're going to do is we're going to take this basic bit here and we're going to duplicate it to create a series of oscillators, or channels if you like, and we're going to make 8 because our speaker array for wave field synthesis, it has 8 speakers in it. How many is that? 1, 2, 3, 4, 5, 6, 7, one more, and 8. So now we've got 8 channels, and if we turn them on, they should all oscillate at the same time. And they might be a bit loud because it's 8 times 0.05 of this same frequency, so it should be louder than it was. And it is. That's still very annoying. Okay, so we've got our 8 channels. We've got our oscillating signal here. So what we need to start doing is working out how to get a delay on the signal. And how we're going to do that is with this function called, or object I should say, and it is called delwrite. Hang on, I'll just move all these over here. Get these out of the way, and take the delwrite function, move it back over here. Right, so we've got delwrite, and then we're going to tell it signal, so tilde, and then we're going to create the variable delay1, and we're going to set the upper limit of delay1 to 1000, which is in milliseconds, so that's 1000 milliseconds of delay time that we can have. So what we're going to do is connect the outlet of that to the inlet of there. And what this tells the program is that there's going to be an object called delread, and we need to add delread to the outlet, or the DAC outlet. The delay1 variable is what stores the delay time So what we need to do is we'll remove that, and oh, I'm in the wrong thing, and we will put an object down here called add tilde, and that's going to add the signal and the delread object. Then we're going to add the delread object in, So we'll put delread, blah, 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 tilde, and delay 1. Okay, but now we need to actually create something that's going to set the value for delread. So the easiest way to do that is to create a number box, which is another type of object or box that you can use in here. So that's going to be adjustable during the program's running. So we'll set the upper limit again to 1000. Lower 0, apply, okay. And then what we're going to do is we're going to connect this all together. So outlet to inlet, outlet to inlet, outlet to inlet, and then out. So what this should do is generate the signal, times the signal by 0.05, create a delay line and a variable which will store the time of the delay in milliseconds, send the signal down, get the delread object, which is the read delay 1 variable, set the delay 1 variable with this number box, add the delay 1 variable to the signal and output. Let's see if it works. We'll just get rid of these. Right, so now we're only outputting from this one channel, if you like. Right, we'll put the DSP back on and we'll see if we can delay the signal. I'll just put it into run mode and we should hear a drop in volume or a raise in volume as we change this delay, because the waves will be interfering with each other. There's a drop in signal there. There's a raise in signal there. And there's a little drop in signal. So we can see that it's delaying something and it's changing the amplitude of the signal that's coming towards us. This is because the waves are interfering with each other and either amplifying because they're in phase with each other, or minimizing the volume because they're out of phase with each other and they're cancelling each other out. So we'll turn that off because we know the delays are now running. And what we'll do is we'll go back into edit mode and we'll get rid of these now, and we'll just duplicate this channel here. So these channels are getting much bigger now. There's more information in them. So we're going to have to extend that like that because the thing's getting a bit big. Right. 1, 2, 3, 5, 6, 7, and 8. There we go. 8 channels, all of them have a delay line on them. So this is done now. We can, I don't know if there's an underline or something. Hang on. We'll be able to put an underline through it. Where's the highlight that one? Well, actually, it's not quite done, is it? Because we still need to do the calculation to get the okay, we won't highlight it yet. Okay, so we've got the delay in. Essentially, what we're looking to do now is do the calculation to get the delay to adjust itself, because we don't want to be sitting with this number box moving it up and down. That's not the function of the program. So what we need to do is we need to put a message box. We need to move the message box. I don't want that to be connected to that. Come on. Right. We need to take this message box, we're going to put it here, and we're going to tell it 340. Right? So, then we're going to add, oh god, then we're going to add a number box, and this is where you're going to put the distance in to the program. So this is the distance box. and this is the time box. So what we need to do is add an object which will divide these. So we're going to say divide, and we're going to give it these two inlets. We're going to give it those two inlets, and then we're going to output to this number box, and that is going to calculate, well, this is going to calculate it, and then it's going to be output in here and sent to the delread variable to set the delay time. So let's check and see if that works. We'll go back out of edit mode, and instead of running the oscillator we'll just leave it off, but we'll test this. So if we set this to 0 first, and then we send the message 340 to here, you always send this message first, and then when we start to move this up we should see the delay time being calculated. So that's working. It's calculating the, oh, this is in meters, by the way. So if we want to stand 60 centimeters away from the speakers, we have to put in 0.6. Or sorry, if we want the source to appear 60 centimeters in any direction away from the speaker, we have to put in 0.6, and that'll make that much of a delay in milliseconds, pass it through and add it to the signal. So that is working. What we're going to do is, instead of rewriting that a bunch of times, we're just going to, I should have just done the one channel and then duplicated it all when it was done, but okay, never mind. There we go, delete all that. Get that out of the way, and then we'll just duplicate this. Duplicate. And duplicate. 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 Again, 1, 2, 3, 4, 5, 6, 7, and 8. Is that 8? 1, 2, 3, 4, 8. Right, brilliant. So now we have this running. We're going to, okay, we can't do anything with it, but we've got that done. So number 2 is taken care of. So we can actually probably just write working now. Now we need to calculate the decay of this. So what we want to do is, we're going to make 2 number boxes. We're going to put them down here to keep them out of the way. But we're going to make 2 number boxes. They're not going to be joined. We're going to put them there. And then we're going to put the object times, so that they get multiplied by each other. There we go. So they're going to get multiplied by each other, and then we're going to output that to there, and we're going to divide that by 1. So we're going to make a divide object. We're going to put that into it, and then we're going to put a message that says one, and that's going to sit there. Oh, and then the output of that will have to go into there. Okie dokie. So that should take the distance and multiply it by itself, and then output it, and then divide it by 1, and you'll get the amplitude decay. So let's try and run that and see if it works. We'll just put 0.6 in there, and we'll put 0.6 in there, 0.6 times by, come on, 0.6, 0.36. Then we're going to divide that by 1, and nothing's coming out because we didn't send this message first. So we'll run it again, hang on. We're in run mode. We'll send this the message 1, we'll do 0.6, because we already know the answer to that, 0.6, 0.6, and we get the answer of 0.36, which I think is right. Let me check it on a calculator. 0.6 times, and then we divide it by 1, 0.36. So we've got the right amount of amplitude decay, and we've got that function working out. So the next thing we're going to do is we're going to duplicate this so that there's one at the bottom of each channel. And finish that off like that. Okay, so that's that done. We'll leave it off there. We've got signal coming through. We've got the delay time being set through the distance. We've got the amplitude decay being worked out by the distance. So the next thing that we're going to have to do is add some sort of a volume slider down here and some sort of meter so that we can calculate the volume of it before we increase it, and then how much we need to increase it by through this. So we'll leave off there, and I'll continue this next time.